Thanks for joining me for this session. My name is Jean-Philippe Bempel. I work for Criteo for 2 years now. But before that, I was in a company that doing some software for financial domain. So we are routing orders to the market. It was a low latency routing orders. So we route orders in less than 100 microseconds, so microseconds, not milliseconds. So at that time, the GC was a big issue. So when Azul came with the Zing JVM with the pauseless algorithm, jump in and put into production since 2012, basically. And since that, I'm trying to follow the trend of the low latency GC and how it works, how they can decrease the pause time of your application. So quick show of hands, who has GC pause issues in production? Okay, couple of hands, so that's the right place to be right now. So if you have questions about this, you can use Slido, code GeeCON 2019 and Rule 9. And in this presentation, I'm warning you, it's deep technical. I'm assuming also that you know about the GC basics, the mark, sweep, compact, phases, and everything for the classical GC. And we will go deep into the concurrent part, the concurrent marking first. That's a common part for the low latency GC. And then we'll study the first GC Shenandoah. Not the first that came up, but I put this order, Shenandoah first. Azul C4, that's a big part because I know more on this algorithm. ZGC, and finally we will help you to choose between those GC algorithms. Concurrent marking. So concurrent marking, it's not new. It's used already in CMS and G1. And that's a constant for all low latency GCs. And they also use the concurrent marking to do this phase. So this phase for concurrent marking is trying to mark all the object graph during the application is still running. And it's based on the tricolor abstraction and used for some the snapshot at the beginning algorithm. So CMS and G1 and Shenandoah use those techniques that we'll explain right now. So let's take an object graph, very simple. You have the GC root that is on the top left. All the objects are white at the first, and then we will color those with 3, white, gray, or black. So when we try to visit this object graph, we visit the first one, the GC root, from the GC root. So we visit and we mark this object gray. And then from this one, we'll visit all the children. So there is only one children, then we'll visit and mark gray. And then as all the children of this the first object are visited, we can mark it black. And then recursively, we go down the object graph, mark all object gray for the children, mark it black once done, and if there is no children, mark it all blacks. So all those objects are lived, and the white object is garbage. It's considered as garbage because, okay, the white object is pointing to an object, a black object, but no one is referencing it, so it's garbage. So the GC will collect them. So when there is a stop of the world event and the GC is alone without the application thread, it's easy to do this kind of algorithm. But if the application thread is modifying the graph during the concurrent marking, we can have some issues. So if we allocate a new object during the concurrent marking, there is 2 ways to handle this case. The first one is to mark automatically the object as black, because this new allocation, okay, this is live because I will just use it right now. Or not considering the new allocation, we will allocate in a certain space, a certain address, that is not considered during the current GC cycle. And we will go to the next one for trying to see if this is still alive or not. The tricolor abstraction gives us some properties for the missed object during the concurrent marking. So the first one is mutator. Our mutator is the same thing that the application thread, that it mutates the object graph. The mutator stores a reference to a white object into a black object. And if all paths from a gray object to a white object are destroyed, we have some issue. Let's take an example. We have the object graph ABC. We are in the middle of concurrent marking. We are at the B. And we have the application thread that executing those lines. So we are storing a reference of C into A. So the object A reference C. And we are removing a reference from B to C. As we are at the B level for the marking, we cannot reach then the object C. And C is still alive because A references it. And the GC at the end of the marking say, okay, C is white object, so it will be garbage. I will remove it. Oops. We have an issue. So we need to deal with it. To resolve this issue, we have two ways to resolve it. So there is a snapshot at the beginning way and the incremental update. Today we will just look at the snapshot at the beginning because it's used for G1 in Shenandoah. So for SATB, the snapshot at the beginning, we'll insert a write barrier. So JIT code will insert a write barrier inside the emitted code for each reference assignation. So if we have like an object X with a field F that store a reference to Y, there is a barrier that will be active only when we do the concurrent marking. And that's a global set. And we do this kind of pseudocode for this. So if the write barrier is active, we'll only if the previous value of the field is different from null, we enqueue this reference to be processed later. So for each reference assignation, we have this kind of code that is inserted by the JIT. So this is the kind of native code, instruction code that it is emitted. So it's kind of something. There is a couple of instructions. The first two is the test. For the test for the write barrier if it's active or not, and then we have a lot of test, and then we have call at the end to a subroutines to do all the enqueuing for the stuff. So it's not free. You have some override of it, but it allows to have a concurrent marking with the application. So that's the way to resolve the issue, because later we'll process those enqueue reference to mark it. That's all for concurrent marking. Now let's go to Shenandoah. Shenandoah is a project that started at Red Hat in 2013. It's based mostly on G1. And it's a non-generational. That's the first for JVM, because most of the all of other GCs for hotspot have been are generational. Shenandoah, there's a choice, deliberated choice for non-generational. There is still option for partial connection, but it's still non-generational right now. It's region-based, like G1. Okay, that's also in constant for all the low latency GCs. And they use a read barrier, Brooks pointer. We'll talk about it and explain how it works. There is also this concept constant for all the low latency GCs, self-healing. So self-healing is the cooperation between mutator thread, application thread, and the GC threads. For Shenandoah in particular, it's only for concurrent compaction. So not for concurrent marking or other phases, it's just for concurrent compaction when they are moving objects from one region to another. So it's mostly based on G1 for concurrent, but with concurrent compaction. The phases for Shenandoah. First one is initial marking. That's the stop of the world phase that scan all the GC routes. And then the concurrent marking that we see previously. The final remark, so we're trying to catch up all the reference that was in queue into the reference queue to be processed and to mark all the missed objects that we have during the concurrent marking. We have a concurrent cleanup, so if some regions after the marking are considered as completely free, we can reclaim them right now as a concurrent cleanup. If not, we need to move some object from a region to reclaim it. So move object from a region to another. That's a concurrent evacuation. And then once we have moved those objects, we need to update the reference so that we can access the new location of those objects. So we need to update this reference. So there is a stop the world pauses. And then for all the object graph, we do it concurrently. And again, for seeking another stop the world phase. Finally, the concurrent cleanup, that we reclaim the region that we have evacuated to be allowed to reallocate new objects in it. We'll focus on the concurrent evacuation because it's a big deal for this. This is the same principle as G1. We are building a collection set of regions that we want to collect, but with garbage first. So we target the region with the most garbage in it to do less work and reclaim faster those regions. We evacuate those regions to release and to reuse. We do the concurrent evacuation with the help of one read barrier, Brooks pointer, and 4 write barrier. Those barriers keep the 2-space invariant. It means that this invariant, it means that all writes that need to happen into an object needs to happen into the 2-space region, so the destination region. If you an object needs to move between from space region to a 2-space, if you need to write into this object, we need to write into the destination. So the Brooks pointer help to the write barriers help to keep this invariant correct. What about the Brooks pointer? So in a JVM, all objects will have an additional forward pointer. It's placed before the regular object. So we have a regular object with a header, and we place the Brooks pointer on top of it, basically, before in the addressing space. And each time we need to access this object, we need to dereference the Brooks pointer to get to the real object. Okay, that's impose a memory footprint overhead and also a throughput overhead, because each time we need to access those objects, we need to dereference. The JIT will limit this read barrier as like this. So we have the reference of the objects basically here with the register and multiply by 8, and then we decrement for 8 the address to get to the Brooks pointer, the square bracket to dereference it, and then we load the real object address into the R13 register. So each time you access one of the field of the object, or we need to go through this Brooks pointer, because maybe the object will be have moved, and then we need to access it at the new location. So during the copy, the evacuation of the object, how it works with the GC thread. We have an object that needs to move from the from space to the to space. We have a GC thread that will handle this, not the application then. We copy the object to the to space, and then we update the Brooks pointer to the new location. That way, if an application thread tries to access this object from the from space, they will dereference the Brooks pointer and then access the object in the to space, in the new location. That's easy. For the reader threads, if we have in the middle of the concurrent evaluation, and we have two reader threads from the application that wants to read into this object. So the invariant is not it's not broken, so we can read directly through the box pointer to the object. The invariant is not broken, so we can do this. That's fine. Now we have two writer threads that needs to write into, for example, two different fields into this object, and then the invariant is broken for this. So each writer thread will copy the object in two different locations. So each writer thread will do the same things, and then we'll try to update the Brooks pointer. Okay, but it will be done atomically with the cast instruction, the comparison swap instruction, and only one thread will win. The other will fail and detect this, and will roll back and discard the copy, use the Brooks pointer, and follow the new location to effectively write into this object. So we have write barriers to ensure this invariant. And for any write, even for primitive, we need to protect and to handle the case where we write into the from space and need to write into the do space. So the JIT for the barriers will emit the code, this kind of pseudocode that was emitted by the JIT. The real code is here. Again, we have another overhead to execute those barriers to ensure the invariant is not broken. So for any write, we have to check if the flag evac in progress, for example, is enabled or not. And then we check if the object is in the collection set of region that need to be evacuated, and then if the object is already copied or not, then we evacuate the object and update the Brooks pointer. There is also three other exotic barriers for ACMP, for the pointer comparison, the comparison swap, and the clone operation. In extreme cases, we have in Shenandoah algorithm a late memory release. It means that we release the region very late in the phases of Shenandoah at the concurrent cleanup phase. So if the region is all completely free, it's done in the first concurrent cleanup phase. But if we need to evacuate some object, we need to evacuate them, update the references, and then we can release the region. During this time, the allocation thread can overrun the GC, and we can end up in a situation where we have some out-of-memory error. So there is some failure mode in Shenandoah. The first one is pacing. Pacing, it means that we basically insert a thread.slip inside the allocation thread to pace this thread and try to catch up for the GC thread and finalize the phases. If it's not working, we have the degenerated GC phase where we stop all the threads, stop the world phase, and we finalize all the phases of Shenandoah during those stop the world phase. So application cannot allocate and modify the object graph. And if not working, regular full GC, parallel full GC to collect all the memory. So when I explain all those, it works up to the JDK 12 or for previous version. So since JDK 13, all the explanation of Brooks pointer, everything, you can throw away into the trash. It's different now. They change, they introduced some changes, very deep changes into the algorithm. So now they change the Brooks pointer, the read barrier Brooks pointer, as a load reference barrier. So now it's not when you access the object you need to dereference. It's when you load the reference. This is subtle, but the reference is big. So when you load the reference, we check if we need to relocate or not the object. So this is a Baker style barrier. So this is a very different way to handle the read barrier. And it's only evaluated at reference load time. When for the books pointer, we dereference each time to get access to the fields. In the same operations, they have limited the forward pointer, the books pointer, so there is no additional forward pointer. Now the forwarding information is stored inside the mark word, and then they remove the books pointer. So we have less overhead with this, but still we have the throughput overhead of all those barriers that needs to be handled. So now, I mean, Roman Kenke was the team lead developer on Shenandoah. So they maybe change the name to Shenandoah 2.0 because the changes are so deep and the algorithm is so different now that we can change the version to 2.0. And they are trying to backport to JDK 8. So the last tweet is from September. So we need to keep up the presentation for those changes. Now we'll talk about the C4 algorithm, Azul. So first thing that comes in my mind with C4 is kind of this, because my dad was in the military. And in fact, Gil, I recently heard into a podcast that Gil Tene, the CTO of Azul, used the C4 as also referencing to this explosive, because when you evacuate those regions, they are blown away. So that's why they use the C4. But marketingly, C4 stands for continuously concurrent compacting collector, then the C4. That's a GC that is generational. So we have the same algorithm for young and old generation. It's also region-based, like Shenandoah and G1. They call it pages. They use also read barrier. The read barrier is called loaded value barrier. There is this self-healing concept also, the cooperation between mutator, application thread, and the GC threads, but at all levels, we will see. The pauseless algorithm that they published in 2005 is real pauseless, but the algorithm. The implementation into the hotspot, because the JVM from Azul is the hotspot based, requires save point, meaning stop the world. There is some stop the world phase into this algorithm. But the pauses that I witness, and since I put this in production, is most of the time under 1 millisecond. So LVB stands for loaded value barrier. We'll talk about this barrier, this special barrier. This is based on Baker's style barrier. It means that when we move objects, when we access those objects that are moved, we get information from forward information table that is stored aside. And this barrier is applied at load time, so as the new Shenandoah barrier, not an dereferencing. And compared to the Baker-style barrier, they fuse also the marking states information into this barrier. So when we check the barrier, we check both marking and relocation state. So the C4 invariant of this barrier ensure that we have marked through to the current cycle the object that we trying to access, and if it is not relocated or not. So if those invariants were broken, we are self-healing the process for application threads. So either we mark the object or we relocate and correct the reference. And each time we load a reference, we check this barrier. But the benefit of checking at the load time is that the JIT can optimize this and say, okay, at the beginning of the method, I will check the barrier for the loading the reference, and then for each access of the object inside this reference, I don't need to check again this barrier. So they can cache, even in a register, this loaded value. So how the LVB works, The state of each object is, for the LVB is stored inside the reference address. So this algorithm works only on 64 bits because references, because we are not using all the 64 bits because it's very, very big. Usually it's more like 47, 48 bits maximum, depending in fact on the OS. And the other bits are used to store more information, metadata information about this. So we can call it also code pointer. And we store like an empty bit. It's not marked through bit, and the remapped and generation information are also stored on other bits. So each time we load the reference, we checked against a global state that give us the current GC cycle and what we expect on the color for those pointers, if this is okay or not. This access to the state is either thread local, so we can benefit from L1 cache most of the time, or into the register. They change the way they store this information. At first it was in thread local, and then they changed to register so they have a dedicated register to store this global state. So they just have to test the current reference address to this register dedicated. So we lose a register, but at least we don't pay the cost of a memory access, even if it is L1. So this is the read barrier, the LVB test barrier. We just have a test between two registers, jump if this is not good, or otherwise load a field. As we store metadata inside those reference addresses, we need to unmask them to access the object, the real address of the object. For that, there is two modes. They use either a kernel module directly. So when you install the JVM, you need to install also a kernel module doing all the allocation for the JVM at the OS level, and also the aliasing for accessing those objects. So the kernel module is able to reference correctly the object, even with the metadata information because of the aliasing. Or use an API, a Linux API that was recently added into the kernel, memfd, and doing the multi-mapping. And multi-mapping we will see with ZGC. Before going further into the algorithm, I would like to remind you the difference between virtual memory and physical memory, and how we can play with it. So we have virtual memory up to 2 power 64, theoretically, and the physical memory, and it's not at the scale here, but we have less physical memory than virtual memory. We can allocate a page into physical memory and back by a virtual page. We can allocate another physical memory and backed by another virtual page, but also we can allocate a new virtual page that is backed by the same physical page that before. So we can have 2 or more virtual pages that point to the same physical page. We can also have a virtual page that is not backed by any physical page. And if we try to access this virtual page, we get a page fault that is handled by the OS, and usually get the real data from the disk. That's the way, for example, that the swap is implemented. Okay, let's move on. C4 phases. There are 3. First one, mark. Okay, marking all objects concurrently. Relocation. We are moving object to release pages. Remap, as we update all the references. So we fix up the reference in the object graph. And as we traverse the object graph, we can do the same for the marking. So finally end up folding those 2 phases together. So as we remap and update all the references, we can also mark the object for the next cycle. So we have this kind of schema where the remap phase of the ground cycle will start the mark phase for the next cycle and go on. For the mark phase is a concurrent marking, but not the same algorithm that we saw before for Shenandoah or G1. This is a precise wavefront marking. So it's a big word to say that's the classic parallel marking phase that we have, for example, for parallel GC, but concurrently. So how we can do this? This is single pass. There is no catch-up to the object graph. So there is no mark or remark phase to catch up the object that we missed or that we enqueue during the modification of the object graph. They, in fact, use the self-healing process. So if application thread try to access an object that is not marked, it will be marked when you access the object. So with an example, it would be easier to understand. We are in the same issue that we have before. We are in the middle of the concurrent marking. We have application thread that try to execute those instructions. And if we go through those instructions, we are storing the C object into A object. So we are loading the reference C. And as we are loading this reference, we are triggering the LVB. LVB, we check this reference. Is it marked or not? No, so we mark this reference and we go on. So this way, we are also, as we are marking, the application is trying to access an object that so it should be live. It marks this object, and we fix the modification of the object graph like this. And at the end of the marking, all objects that needs to be live are marked correctly. Relocation phase. For relocation phase, we do the same. In fact, we select the pages with the greatest number of dead objects, garbage first, and we then protect logically the page that we select to evacuate. So this way, if there is a mutator thread that needs to access an object inside this protected page, the LVB will be triggered. So, and then we move the object to the new allocated page. We build the side arrays with forwarding information. This is an off-heap table. And then if there is an application thread that tries to access an object into those pages, LVB will be triggered, and we fix this by copying this object in the new location, helping the GC, and fix up, use the forwarding pointer and fix the reference. So let's take an example. We have 2 pages. The first one will need to be evacuated. So we have a difference between virtual and physical. We will see why. So we allocate a new page where we receive this, those moved object, relocated object. We allocated a virtual and physical page. We protect logically a virtual page. So each new access will trigger the LVB. We are moving object physically, and this is reflected in virtual also. We install the forwarding table. So each time we access, we can say, okay, we are using this forwarding table to see where is relocated this object. We are releasing the physical page, okay, because we have moved those objects, so it's done. But we still have the mapping for virtual page protected. So if an application thread tries to access an object inside this page, it will trigger the LVB, get the information from the forwarding table, and go through the new location. So we can reclaim this physical page, reuse it, and we can allocate a new virtual page backed by the new physical page that we released. So we can reuse it very quickly, and we still not have remap all the objects. So there is still references inside the object graph that point to the old location. But as this is protected, the LVB will trigger and fix it. So we can reuse this physical page for a new location. So that's the quick release of the pages. So if we think about this, you can trigger this algorithm with only one page free, if all those pages are completely used by your object. So you need only one page as a seed of this algorithm, and go on, go on, go on, release pages, and able to allocate for all the application threads into those reclaimed page. For the remap, very easy. We traverse the object graph, fix up the references, execute the LVB for each object, and in the meantime, the application thread will self-heal the fix-up references using the forwarding information. So each new access will go directly to the new location without fixing up every time the new reference. As we traverse again the object graph, we mark for the next phase. So at Criteo, we are using C4 in production. Why? Because we are using Hadoop cluster, very big, like 2,000 or 3,000 nodes in these Hadoop clusters. And the architecture of the Hadoop cluster needs a name node where all the metadata file information are stored and where they are located inside the cluster. So each data node that needs to locate the file that need to be processed asks about the name node, where are the files. And as we have a lot of nodes, we stored inside this name node a lot of information. So we need to have a heap like 580 gigabytes of heap. We are using OpenJDK 8. And so basically we were using G1. It was very hard to tune because at some point G1 have a fragmentation issue and need to fall back to full GC. Full GC on a JDK 8 with G1, it means that it's serial GC. So there is only one thread that collects all the 580 gigabytes of heap. So it means that we have a stop of the world phase of roughly 30 minutes. So yeah, that's a crash. So we used C4 at a replacement. And since the production, like 2 years ago, we don't have any issue about the GC. So working like a charm. Finally, the GC. It will be quick. It's a non-generational right now. They plan to do a generational version in the next years. I don't know. They are planning to do this. It's region-based. They call it Z pages. It is dynamically sized. They do the concurrent marking, also the concurrent compaction, but also the concurrent ref processing. So ref processing is to process the weak, the phantom, the soft references, or the finalizer concurrently. They use the colored pointer and the load barrier like C4. This is the kind of read barrier that is emitted by the JIT for the ZGC. So again, they are using the register R15 for thread local. So they are not using the register, they are using the thread local state. It's self-healing also, cooperation between Binator thread and GC thread. And it's experimental since the JDK 11. So this is the command line that you need to put to use it. Be very quick because Cliff Click, so that's the guy who was the architect of the JIT for hotspot, and he was working for Azul for a couple of years, maybe a decade at Azul. So he knows a lot of C4, and GPGC is the other name for C4 also, and say, okay, basically it's the same algorithm than Azul, but done by Oracle, and that's true. So it will be quick. So everything you understand to C4, it's the same basically for the GC. So the phases, the name is different, but that's the same. There is an initial mark of the word, concurrent mark and remap. So they are folding also together the marking phase and the remap phase for updating the references. Final mark to think at the end of the marking. Concurrent prepare for relocation. That's the phase where, for example, they are preparing something for the relocation, but also doing the concurrent ref processing. Start relocate. Stop the word phases to start up. Relocate concurrently, and then we're looping back to initial mark because we are doing the remapping during the concurrent marking. So they use a color pointer. They store metadata in a unused bit of references. So 42 bits are used by the GC up to JDK 12. So it means 4 terabytes of heap. Since JDK 13, so the last month, they use 44 bits. It means 16 terabytes. They use 4 bits for metadata, mark 0, mark 1, remapped, and finalizable. This is the schema that you can find inside the sources to see how they use. So we have plenty of place still in the 64 bits addresses. So 42 bits for addressing in this version, and 4 bits of metadata are used. They use the technique of multi-mapping. So color pointer, as for C4, we need to unmask to get to the real address of the object. Some hardware are supporting it directly, natively with instruction, like for Spark or ARM64. But for x86 on Linux and Windows, there will be override to unmask for each access. So as there is only one active view of all the 4 bits of metadata at one point, and that we have plenty of virtual space, we can do a trick of multi-mapping. So it means that we have a physical page backed by virtual memory with one kind of address, for example, 1 bit of metadata marked 0, and we map this with the constant metadata to backed by a physical memory. Then the other metadata is set, so we have another virtual page backed by the same physical page. And then for the other, also metadata information, we have multiple pages backed by the same physical page. So for each phase of the GC, we will be able to access the same data with different addresses. That's why it's called multi-mapping. There is some issue also with this multi-mapping, because it means that we have, from the OS perspective, 3x more memory used as RSS inside the process, so you need to be careful of that. So this is a Jean-Philippe email in the mailing list, say, okay, we have tested for 16 gigabytes of heap for the GC, and we have in RSS like 50 gigabytes used. So for example, if you size your container based on your heap, Java heap, beware of that, because you will get a killer that go pass on your process. So as I said, C4 and ZGC are very similar. So what's the difference between those? For unmasking addressing, C4 using the kernel module, but also multi-mapping, and ZGC use only the multi-mapping or hardware support. For page and relocation, C4 is using page fixed of 2 megabytes, and for large objects, they are not moved, they are not copied, they just remapped at the OS level. For ZGC, pages are dynamic, up to 100 megabytes, and relocation for large objects, no, they stay where they are, like G1, like Among Us objects. They don't move those objects because it's too expensive. But otherwise, basically the same. How to choose between the three? If you need to run on Windows, you have only one choice, Shenandoah, because Shenandoah is supporting a lot of platforms, as C4 and ZGC only Linux and 64. If you want a Battlefield GC, Battlefield tested GC, you can use C4 because I'm using in production since 2012, and it's worked very perfectly. Shenandoah is also ready for production, even though in the OpenJDK they hide the option under experimental, but still it's very mature as a GC. If you want to minimize the pauses outside of GC, you can use also C4 because they have work on other poses like class unloading, the monitor deflations and other things, and write processing also. The GC also, they have work on other kind of poses. And if you don't want to pay for it, you have Shenandoah and the GC because C4 is a commercial license. I put into the slides some references, so I will not go through each of them. I will tweet the slides after the conference. A quick ad. Criteo is organizing a big data conferences, so if you're interested, you can register. It's free, but you need to move to Paris to attend these conferences. And thank you for attending my session. My Twitter, if you want to get a slide. And we'll go through the questions if there are. Okay. So questions? Yeah, I know it's after lunch. Seats are comfortable and it's complicated. Yep. Yep. Good question. For me, none of them. As long as I can say, none of them. So if you are very sensitive to NUMA, my advice is to pin the JVM on only one node. That would be more effective than trying to do some smart stuff. That to deal with NUMA, that's the easiest way to do. Other questions on Slido? Let me get no questions. So you're released. Thank you.